that this picture which I have used, right, this is from David Manloff's book, who is our last speaker, right. So, this is the front cover of the book. Okay, so I have just copied from there. Okay, so as I promised that we will look at some of the results for size versus stability. Okay, so let us look at that. Let us say this is a matching instance. Okay, can you say what is a stable matching here? Correct. So this is a matching, stable matching here, right? What is the size? 2, correct. Let us look at this red edge, red matching edges, right. Do you see any blocking edge here? Size is 3. Do you see any blocking edge? Correct, light green, right. This is a set of blocking edge. So in this with this matching, we can see that there is one blocking edge, right. Okay. Let us look at this matching with 4 edges, right. How many blocking edges are there? 3, right. So we can see that, so these are the matching edges here, okay, sorry, blocking edges here. Okay. So we can see that there is a trade off between size and the number of blocking edges, right. When we had 3 matching of size 3, we saw that this is a 1 blocking edge, right. When we looked at 4 sized matching, then we had 3 blocking edges, okay. Okay. But let us look at it, okay. Is it the only matching of size 3 here? Size 4 here? Okay. So this matching edge has 3 blocking edges, right. But if I look at this matching, right, then I have only 2 blocking edges, okay. So it is not the case that any matching of size blah has exactly the same number of blocking edges, correct. So now what is the question that is meaningful for us? Yes, or maybe we really do not care about maximum size matching. Indeed, one question is what Mohana said, right, that we want to find a maximum matching with minimum number of blocking edges, right. Or we can ask us almost stable matching question where we are looking, we have a stable marriage problem. By the way, the question makes sense even for roommate setting, okay. It is just in this session I am talking about bipartite graph, okay. So now we are asking, does there exist a matching whose size is at least t, right, and blocking edges is at most k, okay. So this is the decision version of the question, okay. Is the question clear to everybody? Now notice that we are not saying find me a stable matching, of course, right, we cannot ask it, right. So we are saying does there exist a matching, right. That is why the notion is almost stable matching. The matching is not stable, but it is close to stability, okay, almost stable, okay. Question for you, what can you say when t is less than equal to size of a stable matching? I am not saying anything. I am not saying anything about k. K is anything, let us say. Do we know the answer? So, okay, do not say, just raise your hand. This is based on whatever you have studied so far. Just raise your hand if you know the answer. Yes?
K should be 0.
Oh, okay. So, like what is the algorithm? How can we find it? T is the size of the matching that we are looking for, right? Now we are saying the value of T is less than equal to size of a stable matching.
So we just use Gilsham algorithm.
Correct. Exactly, right? Just use like just find a stable matching, right? Of course, the size is more than I ask for, which is T, right? And no matter what is K here, right, because the number of blocking edges is 0, right. So, whatever is k, because k is a positive integer, right, k is not negative here, okay. Okay. So, this question we know that it is solvable in polynomial time, okay. So, this question is not interesting for us when t is small, okay. The question makes sense when t is greater than size of a stable matching, correct, okay. So, this question is NP hard, okay, and we will look at it. Okay. So, in general I told you that the question is NP hard, right. Now, what are the meaningful questions when we know that some problem is NP hard, okay. I can ask that what happens when degree is constant, right. Degree means here that the size of length of every preference list is constant, right. So, what happens in that particular case? What happens when the number of allowed blocking edges is constant, right. Okay. So, the first question is NP hard even for degree 3. Okay. For degree 2 we can solve in polynomial time using dynamic programming, okay. We will not see that algorithm. This is also polynomial time solvable, okay. So, the second algorithm is actually simple. Can someone, okay, would you like to think? When the number of allowed blocking edges is constant, then what is the algorithm? Just think and raise your hand. Hint, okay. So, hint is, let us say I tell you what is the set of blocking edge. In the solution magically I am telling you that what is the set of blocking edge. Now, can you do something? So, for example, let us say this green edge is a blocking edge and that is the only blocking edge in my solution. If there is a solution at all, then this is the only blocking edge. Now,
Remove those two and then solve the relation.
those two meaning which two?
Like I assume though they are they are already in the matching.
So, blocking edge is always a non-matching edge by definition. Yeah.
Yes, but if I'm allowing this one, so
Uh-huh.
I'm matching them.
Right.
Remove those people from this set and then start relation P from the beginning.
So, you mean that we delete red and green, red guy and green lady, right? Yes, but we can delete something more. Okay, yes. Do you want to add something? It's not complete. Anybody? So, see, this is a blocking edge, right? So, clearly it is not part of your stable matching, right? What else can you say? Can you match these two red guys? This red guy and red lady? Can you match? If you match them, then this green edge, can it be a blocking edge? No, right? So, pruning is more, not just this much, okay. So, we know that because we need to carefully prune it, okay, before applying our Gale-Shipley, right, because otherwise you delete it, but this red will be matched and you will not get anything. Yes, which are exactly, right. This is the reason we are deleting these red, right. So, if this is a blocking edge, right, cannot be matched with this red girl and this red can also not be matched with this green, correct. So, I can delete these edges, okay, because I know that in the solution this is my blocking edge, right. I do this and now I just find a stable matching, okay. So, what is the algorithm now? Can someone suggest? I told you idea basically, right, but now what is the complete algorithm? Because I do not know this green edge, right. I told you I will magically tell you, but what is this magic? Given the fact that the number of blocking edges is constant, right, try all possible edges, right, okay. Guess the set of, so this is technically this is called guess the set of blocking edges, right. This guess term mean that basically you are going over all possible subsets. Okay. So, we guess the set of blocking edges of size at most k, right. The number of edges is whatever at most n square, right. And then if xy is a blocking edge, you remove x and everybody before x from y's preference list, right, and similarly you prune the x preference list, right, and after that you just find a stable matching in the reduced instance, right. So, if I do not tell you that k is constant here, okay, still the algorithm works, right. Algorithm does not depend on whether k is constant or not, right. So, what will change? Yes. So, value of k you anyway need to vary, right. It does not matter if it is constant or not constant, right, it is at most k, right. So, the effect will be on running time. So, if k is not constant, right, what is the running time? N to the power 2k type, right, and some more polynomial factor, right. So, that is called XP algorithms with respect to k. Okay. Okay. So, for constant k we know that we can solve it in polynomial time. Okay. Now, of course, if the NP hardness has to come, in that particular NP hardness k will not be constant, correct. Okay. So, how many of you are comfortable with NP hardness? How many of you are comfortable? Do you know how to show NP hardness? Okay. How many of you know how to prove NP hardness? So, these are any PhD people. Okay, you do not know? Fine. So, I will just tell you the framework. Of course, I am not going to teach you NP hardness now. Okay. So, to show that a problem is NP hard, right, you take an NP hard problem, right, and then in polynomial time you reduce it to your problem. Okay. Now, what does this reduction means? Okay. It means that you take an instance of a NP hard problem, right. In polynomial time you create an instance of your problem, right, and then you need to show that if this problem is yes instance, right, if this is a yes instance of the problem, then the instance that you have created is also yes instance, right, and if it is a no instance, then it is also a no instance. Okay. So, this equivalence you need to prove. Okay. Then you can show that it is a NP hard problem. Okay. And you can actually, it is easy to believe that by it shows that it is NP hard, okay, or at least it shows that it cannot be solved in polynomial time. Okay. Okay. So, the source problem which I said take a NP hard problem, that problem I am going to take as multicolored clique problem. Okay. I will tell you the definition. So, in multicolored problem, there is again a typo, I am sorry. So, in multicolored problem, I will reduce, okay. So, how many of you know about clique problem? Clique? Clique you know? Okay. So, in multicolored clique basically along with the graph you also have a partition of vertex set, let us say into this k tilde sets. Okay. Now, you want to pick a subset of vertices such that from every vertex class, or you can also call it color class, right, you pick exactly one vertex, okay, right, and this subset should induce a complete graph, meaning for between every two vertices in S you should have an edge. Okay. Is the definition clear to everybody? Right. So, this is multicolored clique problem, right. It is multicolored clique because you can imagine these vertex classes as color classes. You can also imagine in that the graph, right, in the given graph vertices are actually colored already. You do not have, it is not a coloring problem, vertices are colored, right, and basically now you are trying to find a colorful clique. Okay. So, it is up to you how you want to think, how you want to understand it. Okay. It is all the similar notion. Okay. Now, so I need to give a reduction, right. So, let us say that this is an instance of multicolored click problem. Okay. So, we will construct the gadget one by one, and if you do not understand, please ask. Okay. Okay. So, for every vertex in G, we add a path of length 3, say V1, V2, V3, V4. Okay. So, length of a path meaning the number of edges in this path. Okay. So, I construct this. I also need to give preference list, right. So, this V1 and V2 are top preference of each other, right. Now, V2 gives second preference to V3, V3 gives first preference to V2, right, and for V4, for V3, V4 is the last preferred person, right. For now, you just see a path, right, but we will add more things, okay, that is why I have written last, okay. Okay. Now, for every I belongs to K tilde, basically for every K tilde is what? Number of color classes, right. For every such thing, we add two vertices, Pi and Pi tilde, okay. So, for first color class, we have vertex P1 and P1 tilde, okay. Okay. Now, you will connect P1 with V1 and P1 tilde with V4, like this. So, suppose there is also a vertex U in the same color class V1, right, you will add edges like this. Okay. Is this part clear? Okay. Now, P1 has, what is the degree of P1 here? Huh? What is the degree of P1? Okay. So, I cannot of course draw a very large size graph, right, but read the construction. What is the degree of P1?
How do you get the U1 into U1 into U3?
Okay. So, what did we say? For every V belongs to Vg, we add a path of length 3, right. So, there is a vertex V in V1, right. Correspondingly, I have a path. There is a vertex small u in V1 class, right. So, I have this thing. Okay. So, now what is the degree of P1? Yes?
Number of vertices in each color set, like P1 would be the number of colors in the color set 1, number of vertices in color set 1.
Correct, right. So, P1 is the degree of P1 is number of vertices in the set V1, correct. Similarly, for P1 tilde, right. Degree of P2, of course, there will be a vertex P2, right. Degree of P2 will be the size of set V2 and so on and so forth. Okay. Okay. Now, P1 can arbitrarily rank its neighbors. I just fix something. Okay. It is arbitrary, does not matter. Okay. Now, for every edge E belongs to EG, right, we add two vertices, E1 and E2, okay, and just connect them like this. Okay. So, for vertex corresponding to vertices, we add a path on 4 vertices, but corresponding to edges, we add a path on 2 vertices. Okay. Okay. Now, for every ij, right, belongs to K tilde and I less than j, right, we add 2 vertices Qij and Qij tilde, right. For example, I will add Q12, but I will not add Q21. This is just for consistency. Just assume 1. If you want to assume I greater than j, you can do that as well, does not matter. Okay. Okay. So, I add Q12 and Q12 tilde. Okay. I need to, okay. So, my preference lists are missing here. I can't write, right? Okay. So, this is E1, E2, we assume this is also 1, 1. Okay. So, I have 1 here, I have 1 here. Okay. For E1, this is Q12 is the last preferred person. Okay. For E2, Q12 tilde is the last preferred person. Okay. And it will be actually 2. Okay. For E1, I am saying Q12 is the last preferred because I will add more edges to it. Okay. 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 I have it here. Okay. So, now let us say U is an endpoint of the edge E. Okay. Then we add an edge from U3 to E1, E1 and U3 I add an edge. Okay. Now you see I said that I will add more edges. So, these are the more edges. Okay. So, E1 will not be just connected to U3, it is an edge, right. So, it has 2 endpoints, U and other vertex will be in some other class. Okay, so one thing I did not mention, that in multicolored click you can always assume that there is no edge between the vertices in the same color class. Okay, it does not change anything, because anyway you are in the click, you are anyway going to pick just one of them. Okay, so you can say that every color class is an independent set. Okay, so here also if you have even, right, it meaning this edge is between two different color classes. Okay, so its other endpoint is in different color class. Okay, so it will have edge to that as well. Okay, what is the degree of U3 here? Okay, what is the what is the degree of U3 here? Why? Read the read. Degree of U plus 2, exactly, right? Because from U3 you add edge to E1 if there is a edge if U is an endpoint of edge E, right? So this is degree of U plus 2, right? Okay. Okay. Now for this E1, so U3 has lot of edges. So E1 now basically can rank these two neighbors in any order. Okay, I just pick something 2, 3. It does not matter. And similarly, U3 can order its this edge neighbors in any order. Okay, is the construction clear? This is all. That's the construction. We are done with the construction. Is it clear? Now let us understand why are we doing all these things. Okay, because for NP hardness, intuition needs to be clear. Okay, it just come because of that, right? Okay. So this is our gadget, right? Okay. Look at, so what is the stable match? What is the stable matching here? Okay. So if you notice, these purple edges need to be in stable matching. Correct? If this is not in the stable matching, of course, if this is not in the matching, clearly it is not a stable matching. Correct? Because V1, V2, they are the top preference of each other. So they need to be matched. Correct? Okay. Okay. Now if V1 is matched with V2, this happens with everybody, right? So P1 is going to be unmatched. There is no choice. Okay. What about V3? It has to be matched with V4. There is no choice, right? You cannot go and match V4 with P1 tilde. I have not written, but that is the last preference. Okay, that is 2. Okay. Okay. So V3 and V4 will be part of matching. Okay. If you observe, is the unique stable matching here. Yes. But for V4 it is correct. Right, correct. But who are the partners of V3? It is already matched with its top preferred person, right? Right? So in NP hardness we actually try to have a structure which is easy to observe, easy to analyze, right? So now we clearly know that, oh, it's not like there are again exponential many matchings, or it's just a unique matching, right? Because there are some fixed edges which has to be part of every stable matching. After that, matching is basically dictated by these fixed edges in our instance. It does not happen always, but it's happening in our instance. That is what we constructed. Okay, so far so good? Okay. So the instance has unique stable matching. Let's say I need to, okay, I want to construct instance of ASM, right? So I constructed my graph. Now I need to talk about T and K, right? So T is, let's say, this K tilde plus K tilde, choose 2, and this is my allowed blocking edges is also same, let's say. Okay. Tell me how many unsaturated vertices are there in this stable matching with respect to this stable matching. Correct. Unsaturated vertices are these Pi and Pi tilde, correct, and these Qij and Qij's tilde, right. These Pi's I have corresponding to every vertex class, right, and Qij I have, right. How many Qij's I have? K tilde choose 2, right. So these, so all these are unsaturated, right. Okay. So this is the number of unsaturated vertices. Now you notice my T is K tilde plus K tilde choose 2. So essentially I am asking for a perfect matching, correct? Do you all agree? No? Right? So these are the number of unsaturated vertices. Oh, my bad. So this is plus size of mu. Oh, I can. I can't. No, I can. Okay. So basically what I had written was not T, what's the increase I am asking for. Okay. 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 So forget about this. I mean, it's fine. You understand it, right? Just assume wherever I am writing T plus mu is there. Okay. It will unnecessarily waste our time. Okay. So now if you want to find a matching with the desired size, I know I need to match everybody, right? So I need to do this augmentation, right? Q12 will go and match with some E1, E1, E tilde 1, something, right? But Q12 will go and match with one of this edge vertex, correct? First copy of this edge vertex, okay? E2 will go and match with this Q tilde 1, 2, right? Okay. So see, this is important here, right? Now P1 will go and match with U1, okay? U2, U3 will be matched. This augmentation will happen, okay? Because augmentation has to happen, right? Otherwise, how will you increase the size, right? Okay. Now, if I do this augmentation, this E1, E2 will become blocking edge. If I take this yellow edges now, right, then E1, E2 will become blocking edge. U1, U2 will become blocking edge, right. So what do I know? To match one of this thing, right, I introduce one blocking edge. To match one P1, P1 tilde, one pair, I introduce at least one blocking edge, okay. So for every increase, I incur one blocking edge, okay. So this is the reason basically that when you are doing this augmentation, right, so why Q1 tilde 1, 2 will go and match with E2, right. It could happen that Q1, 2 will go and match with E1, Q1 tilde 1, 2 will go and match with some other E2 prime, right, but that will increase two blocking edges and there is no increase in the size. For size it has to be an augmenting path, correct, okay. So this is the only way to increase the size here, okay. Augmentation has to happen, okay, and every augmentation leaves me one blocking edge, okay. But essentially if we try to understand that it's a reduction, right. So if I give you what kind, so currently we are making the observations, what is happening in my gadget, right. But at the end I need to prove that if you give me a solution for click, right, I should get solution of my problem, correct. And if you give me a solution of ASM, I should be able to get a solution for click problem, multicolored click problem, right. So one more thing is that these are not the blocking edges. If you look at this black edge, right, if U3's partner also changed, it is fine, right. But if E1 partner changed but U3 augmentation does not happen, right, augmentation happen on some other vertex in this color class, then this black is also going to give you blocking edge, right, because U3 is, in that case is matched with last person and even prefers U3 more than Q12, correct. But your budget is only K plus K choose 2, K tilde plus K tilde choose 2, right. So, this black edges you do not have budget for these black edges, right. It means that, what does it mean, tell me? What does it mean? You are sleeping on first chair, first row. What does it mean? It means that if you are augmenting here, right, then this augmentation, this vertex augmentation has to happen on one of the, on the endpoints of E, correct. Because if you do not augment on the endpoints of E, then black edges will also be blocking edges, correct, but you do not have budget for them. Do you agree or not? Correct. Preferences between them is arbitrary, right, but this is one and this is last, this is true, right. Preference between the edge neighbors is arbitrary, right, but the first preferred person of E1 is E2, right, and the last preferred person of U3 is U4. Take your time to parse this. So, just think of it like this. I know that there needs to be one augmentation in every vertex class, agree? Let us say, so that augmentation is indeed, that will increase your size by 1, but that will also give you one blocking edge, okay. But, and let us say you augment here, right, but you did not augment on U3, correct. You did not augment on U3, but you augment on some path in the first, corresponding to first color class, right. What does it mean? You, let us say, augment on this path, right. So, that give you one blocking edge, right, but because you did not augment here, right, this is also blocking edge, correct. So, blocking edges is definitely greater than your budget, which is K tilde plus K tilde choose 2, right. This is why if you are augmenting here, you have to augment on the endpoints. If you do not understand, please ask. Okay, so the actually I'll get the intuition. The idea is that we are looking for K tilde sized click, right. So, this subgraph has K tilde vertices and K tilde choose 2 edges, okay. Now, the intuition is that whatever so if the augmentation happens along this edge, I will take this edge in my subgraph, right. If the augmentation happens along this vertex path, I will take it in my click solution, okay. Now, if I take K tilde choose 2 edges, right, and their endpoints, and I tell you these endpoints are only K tilde, then what can be the subgraph? So, I am telling you that because augmentation happened on these edges, right, and pick their endpoints, because I also know that augmentation happened on these points, okay. My goal was just to say that, okay, wherever augmentation happened, corresponding to that you pick edge or vertex. That was my idea, okay. So, Because I know that if you augment on an along an edge, you will also augment along its endpoints, right? So I will pick their endpoints, right? But how many will I pick? I can only pick k tilde vertices, correct? Now a subgraph with k tilde vertices, k tilde choose 2 edges, what it can be? Exactly. Right? Okay, let's look at it formally. So I don't have slides, but we can say it. So did you get the gadget and the idea, intuition basically, right? So we have, now what are we trying to do? We need to show forward direction proof, right? So what do we need to show? Let's say S is a subset of VG, right, which is a click, right? Now what will we do? Look at this, okay? Look at the edges in this subgraph, okay? Okay. No. Okay. So let's say click complete graph is the same thing, okay? Okay. Now it's a graph, I can look at edges, I can look at vertices, right? Whatever edge you have here, augment on those edges. Whatever vertices you have here, augment on those vertices, okay? Let us see if that is our solution. Our solution meaning solution of almost stable marriage problem. Let us try to argue. We need to argue two things, right? Size and number of blocking edges, correct? So what can we say about size, tell me? Can we say that we are increasing by this value? Can we say that we are increasing by this value? Why? Huh?
Because for the each corresponding vertex we have augmented in the vertex side, and the corresponding edge gadget we have augmented the corresponding edges.
Right? Because it's a multicolored click. We need to remember this thing. Okay, we are crucially using the fact that it is a multicolored click, right? Because it's a multicolored click, I know that I have picked one vertex from every vertex class, right? So because of that, I know that for every vertex class I do this augmentation, right? One augmentation, right? So I know that I have saturated all PIs and all PI tildes, correct? Right? And it's a click, right? So I also know that we have saturated, because between every vertex, every two vertex classes, you have one edge in your GS. Agree or not? Yes, because it's a click, multicolored click, right? Okay, so because of that, I know that I have saturated all QIJs till down, right? And clearly, I did not unsaturated any of the previous vertices, right? So it is indeed a perfect matching, which I was looking for. So size wise, we are good, right? Now we need to argue about blocking edges, okay? Because it's again multicolored click, I know that from every this vertex class, I just augment on one path. So from every vertex class, I just get one blocking edge, okay? Because it's a multicolored click, between every two color classes, I just pick one edge, right? So in this edge gadget also, I just get one blocking edge, okay? So far I know that I have k tilde plus k tilde choose two blocking edges, correct? Okay, but why do I not have other blocking edges? Okay, this we need to argue, right? Okay. Where can I have other blocking edges? Let us ask that. Okay. U1 I already have this one blocking edge. U2 is matched and one blocking, there is no other edge. What about U3? I don't know. U3 is matched to its first person, correct? So there is no blocking edge. Okay. What about U4? Because U4 is adjacent to just P1 tilde and U3, so one of, and U3 is matched to first person, so this is not a blocking edge, right? And this is a matching edge, so fine. So with vertex wise we are fine. Okay. Okay. So for this P1 we do not have blocking edge because all the other vertices like U1, V1, right, they are anyway matched to its first preferred partner. Okay, so there is no other blocking edge. Correct? Okay. What about QIJs? Same story with QIJs. Okay. Now what about E1? E1 is the thing that we need to carefully observe. Okay. So E1 is matched with its last person. Correct? So indeed E1, E2 is a blocking edge, we counted it. Right? Why these are not the blocking edges? Use the fact that it's a click.
They are matched to their first partners. Corresponding U3 is matched to their first
Right?
partner.
And it happened because it's a click, right? I know that if E1 is an edge in my click, its endpoint is in my S, right? Right? So I know that I have augmented on U3, its endpoints. So I know that its endpoints are matched to its first person, right? So these black edges are not there, as blocking edges, right? These black blocking edges are not there, right? Because if E is in my click, then I know its endpoints are in click, right? By the definition, right? So if E1 changes the partner, right, then U3 its endpoint get matched with first preferred person, right? So it cannot be a blocking edge. Okay. So the only block, and what about E2? E2's degree is only 2. One of them is contributing to blocking edge, one of them is contributing to matching edge. What about Q1 2 tilde? Same as P1 tilde, Q1 tilde. Correct? Right? So if you have a click solution, then we also get a solution for ASM problem. Is that okay? Now we need to argue reverse direction. Okay. So how much time I have? Oh, 5 minutes. Okay, it's okay. We have 20 minutes break today. So look at the reverse direction. Okay. It means that I am giving you a solution of almost stable matching, right? It means that I am giving you a matching whose size is this T, K tilde plus K tilde choose 2 plus size of a stable matching, and the number of blocking edges is K tilde plus K tilde choose 2, right? So we have already argued that if you want to have a matching with this size, it has to be a perfect matching. Okay. So I know that in my solution matching, right, let us say eta, all the vertices are saturated. Okay. Because all the vertices are saturated, so what do I need to show? The thing that I wrote it here earlier, right, that, okay, so what will we do? So we know that Q12 is saturated, right? Q12 is saturated, right? So Q12 is saturated with some E1, right? Q1 is matched with some E1, okay. Then E2 will go and match with Q12 tilde. You may ask actually here why E2 will go and match with Q12 tilde, but we already argued, right? Q12 tilde has to be matched with someone, right? If it does not go and match with E2, it will go and match with someone else. Let us say E2 bar, E2 tilde, right? So it will incur 2 blocking edges in this one particular class, but we do not have budget, right? It's a solution, so it is within the budget, so it cannot do so. Okay. Okay. So this will happen. Okay. Same thing happened here also. Okay. So now I only need to say that in my solution, if this is an augmenting path, right, then in the vertex class its endpoint, right, you have augmenting path on its endpoint, right, and why this will happen? Again, because you do not have budget to have this blocking edge, right? So now what is my solution in ASM? Whatever, if this change the path, then this is in my GS, right? If this change the path, then this vertex is in my GS, right? So I know that only k tilde may change the path here. I know that only k tilde I choose to change the path here, right? So I pick right, and I know these vertices are endpoints of these edges. Okay. So as we argued that if you pick it like this, it has to be a click. There is no other option. The graph structure has to be this. Okay. Any question? So this NP hardness was already known. Okay. But this particular reduction, this is from one of our paper. This tells you lot of things. Okay, it just does not tell you that it's NP hard, but it also tells some other hardness more than that, just NP hardness. Okay, it will tell us that under some assumptions, right, we cannot hope for certain kind of exponential algorithms as well. Okay, we will look at that, right, in second session on the same thing. Okay, so maybe we can take a break and come back at 11:20, 11:10, 11:10. Okay.